Hello, I'm Lin Luo from SketchX Lab CVSSP at the University of Surrey. I'm going to represent our work towards 3D VR Sketch to 3D Shape Retriever. In this work, we study 3D VR sketches as a new input modality towards shape retriever, and we provide some insights into this new problem. There are two common scenarios for 3D shape retriever, with the query being 3D or 2D. Obtaining and getting access to 3D queries such as 3D scans or 3D shapes is a problem on itself. Another option is to use 2D queries such as images or fast sketches. Obtaining such type of inputs is much easier, yet the gap between 2D and 3D data representations limits the retrieval performance. In our work, we advocate 3D Sketch as a new modality towards 3D shape retriever. 3D Sketch allows to represent the shape directly in 3D, and thus the domain gap is smaller compared to 2D sketches and images. It is relatively easy to acquire compared to 3D shapes or scans. Our vision is that one can sketch in their environment any shape they have in mind with the hand controllers, and then use it as a query to trigger the retrieval process. In order to study the 3D sketch to 3D shape retriever, we collect a set of human VR sketches to test our models. Moreover, we propose an approach to generate synthetic 3D sketches to train our models. We code VR interface, which we use to collect 3D VR sketches based on Oculus Rift platform and Unity engine. Users load a reference 3D shape and draw lines on top of it using hand controllers. They can hide the reference shape at any moment. We collected the first set of 167 3D VR chairs and desktop sketches from 10 participants without art experience. All sketches are paired with reference shapes so that we can use these sketch shape pairs to evaluate the retrieval performance. These are example sketches we collected. We observed that different participants sketch in different styles and with a variable level of details. We also found the two key properties of 3D sketches. One is sparsity. 3D sketch is composed of sparse lines. The second is abstraction. 3D sketches are simplified and often geometrically inaccurate. Since the collection process is both time and cost sensitive, to get enough samples for training the retrieval models, we propose a novel approach to generate a synthetic dataset of human-like 3D sketches. A key trait of our generator is that it can produce 3D sketches with different levels of abstractness, mimicking the variability of level of details found in human sketches. First, we extract from a reference 3D shape a detailed curve network with flow wrap. In this step, we extract a very detailed curve network that preserves well-shaped details, which are, though, uncommon for human novices sketches. To obtain a more human-like sketch appearance, we focus on two aspects: level of detail and mechanical inaccuracies. We first perform details filtering and lines consolidation. We then break the long curve chains into shorter strokes, to which we apply a set of local and global transformations to achieve a variability of style inherent to human sketches. The sketch abstractness can be expressed in terms of one single parameter, level of abstractness, where the higher the value, the more abstract is a sketch. We generate 5 levels of abstractness and study the effect of abstractness on the retrieval performance. We compile several common settings for shape retrieval models through training on our synthetic dataset. There are 3 main questions we try to answer, including what's the best representation for 3D sketch to 3D shape retriever, the effect of abstraction levels, and whether 3D sketch queries can result in a better retrieval accuracy than 2D sketch queries. When dealing with 3D shape retrieval from a single image or 3D shape, existing work is divided into 2 large groups based on the shape representation used, view-based and volumetric-based. Due to sparsity of a 3D sketch, among the volumetric shape representations, we opted for point-based. We compare the common multi-view-based and point-based approaches for 3D object representation. which are View N-gram network and PointNet++. We experiment with different rendering and point sampling strategies. Triplet loss are commonly used in retrieval tasks. It is to ensure that the anchor negative distances are larger than the anchor positive distances by a given margin. Here we consider both sketches and shapes as anchors. Positive and negative samples are shapes or sketches from the same class or different classes, respectively. In our work, we evaluate both standard triplet loss and its variant, triplet center loss. Triplet center loss represents the state-of-the-art for 3D model retrieval, which we refer to as TCL. All our models are trained with classification and contrastive losses simultaneously. For view-based method, we compare two types of architectures. One is cell-mix, in which case the sketch and shape share encoders, and heterogeneous, in which case the sketch and shape do not share encoders. For volumetric-based model, we use the cell-mix network. The feature vector is a 512 dimensional vector in both view-based and volumetric-based cases. To account for a variation of human styles, we propose an architecture with an additional sketch regularizing branch that evaluates an additional reconstruction loss. As a reconstruction loss, we use the transfer distance between an input 3D sketch with a given level of abstraction and the 3D curves network. We conduct a series of experiments on these models to drive out some insights. Here we show quantitative comparisons between view-based and point-based approaches. The x-axis means using different level abstractness synthetic sketch as query. The y-axis is a mean average precession. We show that on the task of 3D sketch to 3D shape retrieval, point cloud representation, which is the dashed line, beats multi-view approaches, which is the solid lines, which may due to better handling the sparse and abstract nature of 3D VR sketches. We additionally compare the performance of the 3D sketch-based retrieval models to the performance of a 2D sketch-based retrieval model. We use View N-gram network as a backbone to build the 2D sketch to 3D shape retrieval baseline, where we use View N-gram to encode 3D shape and the additional branch to encode the 2D sketch, which is a common practice for 2D sketch or image-based retrieval. The figure shows that the 2D sketch-based retriever is outperformed by all the baselines for a 3D sketch-based retriever, advocating for the 3D sketch-based retriever. We also compare triplet loss and triplet center loss for class level and fine-grained retrieval performance. We observed that the MAP of triplet loss and triplet center loss on our problem are comparable, while the top 1 accuracy is much higher for the triplet loss, showing that triplet loss learns better inter-class variance and is more suitable for the fine-grained retriever. We further show that adding regularization branch leads to a superior performance over all the considered baselines. The reconstruction branch improves the MAP values for the triplet center loss, while the MAP values for triplet loss are similar with and without the reconstruction branch. Both result in top performance. In top 1 scores, the regression branch significantly boosts the performance of the triplet loss, resulting in the top performance on human dataset. Here we provide some visualizations of retrieval results for 4 main baselines on our collected dataset of human VR sketches. In summary, in our work, we show that volumetric-based representation is more suitable for 3D sketch to 3D shape retrieval than view-based representation. We show that abstraction of human sketches has to be taken carefully into account when designing the model for 3D sketch to 3D shape retrieval. In our work, we propose the reconstruction branch that aims at the regularization of the input sketch. We compare 3D sketch to 3D shape retrieval to 2D sketch to 3D shape, and show that the 3D sketch query allows to obtain more accurate retrieval results. Finally, we compare two commonly used contrastive losses for retrieval tasks, triplet loss and triplet center loss, and show that triplet loss learn better inter-class variance and is more suitable for fine-grained retrieval. For more information, please refer to our project page. Thank you for your attention.